Thank you, Andrew. Thank you, Ian. And thank you to the Institution of Structural Engineers for inviting us to give this year's James Sutherland Lecture. The Clifton Suspension Bridge is probably one of the best known bridges in the country, if not the world, and it is a symbol to the City of Bristol. Nonetheless, we've been overwhelmed by the level of interest in tonight's lecture, so I hope we can provide something of interest to everybody. We've had quite a challenge trimming it down to just 1 hour, as you can imagine. My colleague Aegon will talk about a sample of planned works that we've undertaken over the past decade. I'm going to talk about one that very definitely wasn't planned. And Bob is going to talk in detail about a geotechnical investigation that has spanned most of the past 10 years. But before we proceed, I would like to take a moment for a dedication. Last November, one of our trustees, Alf Perry, passed away unexpectedly. For those of you who didn't know Alf, he spent most of his career with Arup, with a varied career in design of buildings worldwide, but it was his passion in 19th century engineering history for which we knew him best. Alf had a significant hand in everything we are going to talk about tonight. He either instigated it, championed it, or scrutinized us to make sure we were getting it right. Those of you in the audience who are consulting engineers will know that there's nothing more gratifying than getting it right to the satisfaction of an intelligent client. That was Alf. Alf was a great trustee. He was an absolute encyclopedia of knowledge on the Clifton Suspension Bridge, and his recall was amazing. I envied him for it. We cannot overstate his contribution, passion, and commitment to the bridge. As I get older, I realise that good things happen because talented and passionate people make them happen, and that was Alf's approach. I'm sure that for as long as we are involved in the Clifton Suspension Bridge, we will apply the test. What would Alf say? What would Alf think? So with that in mind, we would like to dedicate our lecture to his memory. A little bit of background to the bridge for those of you who are not familiar with it. It was opened in 1864 and is credited to Isambard Kingdom Brunel, although he died 5 years before it was completed. He oversaw the construction of the abutments, towers, and anchorage tunnels. But many believe the bridge should also be credited to Sir John Hawkshaw and W.H. Barlow, the engineers who saw the design and construction of the suspended structure through to completion in 1864. It's worth noting that the chains and saddles came from Brunel's Hungerford Bridge, built in 1845. So although the bridge has been open for just over 152 years, many of its components are much older. If you are interested in the origins and history of the bridge, I suggest you talk to Julia Elton, James Sutherland's widow, who gave an excellent lecture here last year on the origins of the bridge and who is responsible for its design. The bridge is operated and maintained by the Clifton Suspension Bridge Trust, incorporated under the Clifton Suspension Bridge Act of 1952. There are 12 trustees, one from each of the local authorities on either side of the bridge, and 12 from the great and good of the wider Bristol area. They bring a wealth of experience across a range of sectors to enable this bridge to continue. They employ a full-time bridge master, and we're delighted that Trish Johnson is able to join us tonight. She has a staff of 24, most of whom are attendants because the bridge is open 24 hours a day, almost every day of the year. Some admin staff and a small maintenance crew. It's the Trust's aim to preserve this bridge in perpetuity, no 120-year design life here. And to maintain its use by the public, and to provide information and facilities for the enjoyment of visitors to the bridge. We'll talk a little about that later. As you would expect, it is Grade 1 listed and has been since 1959. And it's not just a historic monument, it remains a key part of Bristol's infrastructure, linking Clifton and Lee Woods. It's open to pedestrians, cyclists and motor vehicles up to 4 tonnes gross vehicle weight, and the vehicles pay £1 for the privilege of crossing. Flint Neill, now rebranded as Covey, as Ian mentioned, were appointed in 2006 when the incumbent Howard Humphreys was taken over by Kellogg Brown and Root. They decided they didn't want to do bridges anymore and resigned their commission. I can assure you there's no danger of that happening with Covey. I'm now going to hand over to Egan, our project manager for this job, and he's going to take you through some of the more significant planned works we've undertaken over the past 10 years. Egan.
Good evening. Yes, as John mentioned, there's probably many things I could talk about on this bridge because I have been involved with it for just over 10 years now. But the presentation tonight is going to focus on some of the bigger planned maintenance projects that have taken place on the structure in the last 10 years. And the first one I want to just introduce is carriageway drainage and resurfacing, and that was done on site in 2008. But before I delve into the detail, I just want to give you a quick introduction to the deck. And this is a cross-section of the bridge deck, and just so you're familiar with some of the terms that I'll be referring to. Here you can see the vertical hangers. I will try and point them out. And they're connected at their upper end to the main chains, and at their lower end to the top of the longitudinal girders, and there's 2 of them there. The lower end of the longitudinal girder is bolted to this lattice cross girder, and on the outer edges of the cross girder you can see this lattice parapet girders, which have got cast iron stanchions here to provide some lateral restraint. Now the carriageway deck is made up of 5-inch thick Douglas fir timbers which span longitudinally, and on top of that you have got 2-inch thick Douglas fir planks that are nailed in a transverse direction. Now the carriageway running surface is a mastic asphalt consisting of a paving layer on top of a thin waterproofing layer. The vast majority of all the structural elements on the bridge are still the original wrought iron, although some hangers and some connector plates have been replaced in steel over the last few decades, really. Now the exploded view on the left there is just shows the connection between the longitudinal girders and the cross girder. It's a very important connection. It supports the deck, and it has got 8 bolts acting in tension. Now unfortunately this detail had suffered a bit from corrosion just because of its position, and the elements which I've highlighted in orange and blue, and the 8 bolts also, and the lower angles of the longitudinal girder had all suffered corrosion, varying in severity across the bridge, but it did need some action. And the main reason for that was kind of down to this detail here, which I've highlighted in a pinky purple colour, and that consists of a timber curb with brackets out the back and this timber splashboard, and that was a detail that was installed when the bridge underwent a major refurbishment in the 1950s. The problem with it is it wasn't very effective at keeping water out and protecting the connections down below. And the photograph here with the splashboards removed shows how dirt and water was sprayed from the carriageway by the passing vehicles, and it all found its way down onto the web. It was exacerbated really by the fact that the carriageway had suffered significant rutting under the wheel tracks. So when it rained, I mean this example here, they were power washing the girder, but when it rained, the water collected in the wheel tracks and couldn't find its way to the drains. So the vehicles sprayed it onto the girder, but it also worked its way along the bridge and found its way down to the movement joints at both ends, and also caused quite a significant amount of timber rot and corrosion to the steelwork. And that's just an example of some of the connections close to the articulation span, which had suffered quite badly from the corrosion. So this project, the main focus of this project was to either repair or replace some of the badly corroded sections, also to replace that curb and splashboard detail with a more waterproof or watertight alternative, and also to renew all the surfacing on the carriageway. The photographs here show some of the metalwork repairs in progress, and I just want to point out this, just talk a bit about this. This is where the plan bracing comes in and connects to the cross girder. What has been removed here is the connection plate that attaches and connects the cross bracing. We were replacing that because we could see there was significant corrosion at the top of it. You know, it lost probably 50% of its section, cross section. When we removed the plate, we discovered that there was actually a significant amount of corrosion to the underside as well, and it was all because dirt was getting trapped in the voids underneath the plate and was causing it to corrode from underneath. And that was probably another 25% section loss. So the plate was very thin in places. They were all replaced, but that did trigger the question, is this happening somewhere else? Is there corrosion happening to surfaces which are hidden from view? So that's something that we have kept in mind. There are similar details on the bridge, but most of them, or pretty much all of them, are not exposed to this level of wetting, irregular wetting. Put up these photographs really just to give you a bit more of a view into the construction of the deck. This is where we reconstructed the bridge deck at both ends where the movement joints are positioned, and that was because of the rot and the corrosion that I had mentioned. So you can see the main timbers there and the plan bracing. That's the gantry, underbridge gantry underneath, which provided a very useful platform for the works, and you can see the men there installing the new timbers. Photograph here shows the final detail. It's nothing overwhelming, but it is a linear drainage channel, runs the full length of the bridge. There are openings in the curb which allow water to drain from the carriageway into the channel, but this feature here, which is an overhang which is bonded to the web, diverts any spray from the carriageway, and essentially we've hopefully created a relatively watertight detail here which protects and will preserve the wrought iron below. In fact, the detail is actually very similar to what was installed when the bridge first opened, except they had a copper drainage channel. Then we've put in a glass fibre composite. Just wanted to point this out. I do find this a bit of an amusing photograph. Just really the scale of the bucket and the JCB telehandler. The reason for that is the 4-ton weight restriction on the bridge. Usually that telehandler would be a 22-ton version, except this one is a 4-ton version, carrying a partially filled bucket to feed this hopper, which is laying the extruded asphalt curb. And by coming up with that arrangement with the contractor, we managed to comply with weight restrictions. So now that we had kind of installed a water, or improved the waterproofing of the bridge deck, we were able to move on to some of the underdeck painting. This underdeck painting of all the cross girders, plan bracings, some of the parapet girders commenced last year, and as part of that work we are raising the the footpaths. So they are lifted in 16-foot sections and put onto temporary supports. So we're doing half the bridge at a time, so only one footpath is closed to the public. So that started last year on one half and will continue this year on the second half. Next few projects involve a lot of masonry, and there is a lot of masonry on Clifton. You can't help but notice it. It's quite imposing. That's the abutments, which are made of red sandstone, and the towers, which are largely pennant stone with some batstone plinths and pillars at the top, which support cast iron roof. This started in 2010, phased over 3 years. The phasing was largely to put it into kind of manageable chunks. There's a lot of masonry to cover, and looking to involve specialist masonry conservationists. And it was broken into manageable chunks of just over 1,000 meters squared per annum. And I guess the main driver was that significant maintenance of the abutments and the towers hadn't been undertaken for quite a few decades. And inspections had identified that there were certain areas that needed attention, and it couldn't really be put off for much longer. Also, the last time the major repointing works were done, they did it all in cement mortars, which started to have an impact on the softer red sandstone. Of course, the bridge, being in its perched elevation, it's not the easiest to access. There was no ground-bearing scaffolding here. So it was a combination of cantilevered scaffolding from the footways, but not so much that they impeded pedestrian flow across the bridge. And also these gallows brackets, which were made up and secured to the abutment, and from which then the scaffolding could be constructed. So in this photo here, the gallows brackets are about this level, so you can see that much above and that much below hung from it, all installed with rope access technicians. So it is a very substantial part of the works. I should just acknowledge the involvement of Ferguson Mann Architects, who are the specialist conservation consultant, and they're based in Bristol and have an involvement with the bridge that dates back quite a few years also. Much of the stonework conservation was what you'd expect. There was some high pressure steam cleaning, removal of thousands and thousands of meters of cement pointing and repointing with lime mortars, all of which were approved, heritage approval, removal of large calcite build-up, and this is a mason putting a tool finish to a masonry, a block which was going to replace something similar to that. It mightn't be that actual location. What followed on after that went to the towers. The towers, again, were done in a phased approach, 2 years, one for each tower, quite logical. It involved a loss of masonry conservation again. I think there's over 1,000 meters squared again in each tower. But also the refurbishment involved repainting of the cast iron parapets here, which are very distinct to the bridge. Involved painting of those. There was quite a bit of refurbishment to the drainage system also in the tower. A lot of access improvements, waterproofing to platforms. And yeah, so all of that was done to the towers. Just one item that I wanted to just talk a little bit more about on the towers. The batstone pillars, which you can see towards the top of the tower, and they support that cast iron parapets at the top. You can see the writing there, which is very prominent when you go to view the bridge. But it suffered, these batstone pillars, it suffered a lot in terms of cracking. And this, we found records that dated back to 1920 when they were reporting the same problems. Joints opening up, cracks appearing, and they were sending people up to repoint. We did some investigations and kind of came to the conclusion that it was corrosion of the embedded artwork that was the cause, very obvious. This is one of the culprits that we removed during the works, but we installed an impressed current cathodic protection system, and that was designed and installed by Rowan Technologies. Now, I couldn't do this presentation without mentioning the abutment vaults. That's the leadwood abutment vaults. Not only because Bill Harvey's sitting here in the audience, but also it's a very good example of how knowledge can get lost, particularly if records are not established and maintained. In 2001, the Trust commissioned a number of core drilling, undertook a lot of core drilling through the abutment structure, and also a significant amount of ground penetrating radar to try and establish the makeup of the leadwood's abutment, because there are no record drawings. Nothing exists of this abutment. And they finished in 2001 and concluded, quite unfortunately, that it was solid. Now, the ink had barely dried on the report when the Trust were also doing some repaving work at the footway level around the base of the tower and discovered quite a deep vertical shaft. And what followed from there was an abutment full of voids. Now you can see in the sketch here that there are 12 vaults, 7 in the upper level, 5 in the lower level, and I just acknowledge Bill Harvey's involvement in this, and he has been involved in this inspection of all the vaults, since access has been provided. And providing access has actually been the focus primarily for the last 10 years, because it's still difficult access. A door has been installed in this position, but many of the vaults are still confined space entry. And it was only in the last year that access to these 4 lower corner vaults was achieved. It was using a technique of vacuum excavation, which managed to clear all the rubble, obviously, that the construction team decided to dump into the tunnels, linking into a lot of those lower shafts. So finally cleared and made way for Bill and his son Hamish to crawl through the tunnels and carry out an inspection. And there's just done that in recent months. Also undertaking a pine cloud survey, and so now we've got very detailed information about the makeup of the vaults, and there's also a lot of photographic information as well, which assists with the assessments, and no doubt Bill will give more detail on that in future presentations. As John mentioned earlier, one of the main goals of the trustees is to provide information, for visitors to the bridge. And in 2014, to mark the 150-year anniversary, this visitor information centre opened, and it's sited in the bridge maintenance compound. It is an absolutely excellent facility. Lots and lots of information, great posters, and I'd highly recommend that you visit here and spend some time here the next time you're in Bristol. And with that, I'll hand back to my colleague, John.
Any better if I talk closer like that? Yes, no? Okay, I'll speak up as well. So the next few slides are going to cover an item that very definitely wasn't planned. On a Saturday afternoon in April 2009, a member of the public found this, a broken hangar, close to mid-span on the north side. Now the hangars, as Egan has mentioned, connect the longitudinal girder of the deck to the chains above. Each hangar consists of a pinned connection at the bottom through an eye, to a bottle screw that provides some adjustment on length, then a solid rod up to another pinned connection at the top. At the time of the failure, almost every hangar on the bridge was original and made from wrought iron. And you can see that they're designed to work as simple pinned tension elements. Thankfully, Howard Humphreys had established that the bridge could sustain loss of one hangar with a pair of 2.5-ton axles on the cross girder adjacent to the failed hangar, but with no factor of safety remaining. So the first thing we did was to cut a temporary hangar from a piece of S355 steel and put it in quickly. It enabled us to reopen the bridge, remove the traffic management, and then sit back and think. So why did it happen? Well, the deck has a small hog to its profile. And as the sketch shows, if you provide or apply asymmetric live load, it tends to flatten that profile with the effect that the deck pushes longitudinally. So there's this relative movement between the chain and the deck. And that movement is accommodated by rotation of the hangars. And of course the rotation is greatest where the hangars are shortest. But our upper pin seized in the failed hangar. So a hangar that was supposed to do something like this was now clamped at the top, and that attempt for the deck to move resulted in bending and fatigue. So as a result of the failure, we learned something about the bridge's actual behaviour, not its designed intent. The photograph on your left was taken 2 days after the failure. And you can see the grey region is literally the last thread, the amount of metal that wasn't quite enough to hold on to the dead load in the hangar, the tension in the hangar. But you'll also notice that the fatigue surfaces are corroded. And this is because this fatigue failure took a very long time to happen. So having restored structural support, we decided we should look at all of the other hangars. Remember, they were all original and all wrought iron. One of the key appointments we made was an appropriately experienced NDT practitioner. And what do I mean by appropriately experienced? Well, this individual, Paul Sutherland, understood the material. If you carry out magnetic particle inspection on wrought iron, you will get a lot of indications. And to a less experienced practitioner, they would look like cracks. They're not. They're simply characteristics of the material. So he had the unenviable task of differentiating between a characteristic and a true defect. And we've got some of them here. A quite significant transverse crack, surface breaking defect, a longitudinal split in a hangar, and a split through one of the bottle screws. We think this is grease that has leaked through from the inside. That crack goes full thickness. So inspection of the hangars proceeded on the basis of perceived vulnerability. All the hangars have the same criticality. So we looked at the threads and changes of section on the middle third hangars, the ones that we expected to rotate the most first. Then the upper and lower connections of the hangars in the middle third, the body of the hangars in the middle third, big focus on the middle third, and then we moved out and looked at the remaining hangars. This photograph shows you why the articulation was lost. You can see the corrosion on the face of the eye, and that rust occupies a far greater volume than the wrought iron that produced it. So you can imagine how that has jacked against the pair of female plates and created a pressure that has resisted attempts for the hanger to rotate. I should say we took every hanger out in turn to see what articulation it had, and this was quite a typical finding. The next photograph shows a refurbished lug. We've cleaned it, we've thinned it slightly so that it will go back between those two female plates with a bit of space. And when we put it back in, we put PTFE washers on either side to try and make sure that articulation is always there. But in investigating this particular failure, we found evidence that there had been problems before. A trawl of records showed that between 1978 and 1985, hanger articulation had been addressed. We often talk about the generation gap in engineering, that we're due a failure once every 30 years, because that's how long it takes for a group of engineers to retire without passing on their knowledge. And it's a similar kind of scenario here with Clifton. You can see that the original hanger eyes had ovalled, so they'd taken them out and they had filled the original eye with weld metal, and they had then re-drilled it to a smaller diameter and put in bearings that required lubrication, but the need for lubrication had been forgotten. The bearings had perished and the holes had started to oval again. As a result of this failure, we are now very much better at record keeping. We've invested a lot of time and money in a strategy for ease of access for future generations. And I think it's fair to say that this will be very much Alf Perry's legacy for the bridge. I should add that we refurbished 7 out of the 162 hangars, and we replaced a further 10. I'll apologise to the purists because we replaced 10 hangars with steel versions. But we took an enormous amount of care to replicate the geometry and the details of the original wrought iron versions. I can't tell which ones we've replaced and which ones are original without walking along the bridge with a drawing. But the photographs show hangars going in and the care we took to forge the eyes as they would have been done originally, again to try and replicate the geometry. This table summarises our knowledge at the time of the hanger failure, and it was based on previous risk assessments. Until the hanger failed, we derived a great deal of comfort from what we thought we knew. Note that the hangars had been assessed for fatigue, but that assessment presumed that the articulation was present. I think it's fair to say that the hanger failure tested the trustees' nerve and shook their confidence. So we now do a very regular routine qualitative risk assessment. We look at availability of structural information, ease of access for inspection and maintenance, vulnerability to deterioration, and of course structural capacity. But it's a live and dynamic document, and we're always thinking very carefully about potential failure modes. How might the behaviour of the bridge change given that it's getting older and deteriorating? This table also shows what we didn't know. We didn't know anything about the capacity of the land saddles and the anchorages, although it was clear a lot of work had been done about 100 years before. And although we knew something about the foundations, we deemed that it wasn't enough, and Bob McKean is going to talk about that in a moment. But having had a failure through loss of articulation, our immediate thought was, well, where else could we lose articulation and how significant could it be? And the obvious place is, of course, the saddles at the top of the towers. So this is the arrangement. The chains come in from the main span and the land span, as it's called, and they sit on a bed of rollers which should allow free movement from left to right, so that the horizontal component of the tension in the main span and the land span balance. After the hangar failed, we installed instrumentation on all four to confirm that they're moving and to continue to confirm that they're moving. And I'm pleased to report that they do. One of them drags its heels a little bit, but for the most part they behave. We've stepped up the inspection and maintenance requirements for the saddles, recognising their importance. They've been cleaned. Here's Aegon inspecting them by endoscope. And the photograph on the left shows the rollers with the keeper plate removed, but once that is put back in place, there is now a perspex cover to prevent debris getting in and hindering the articulation. So what would the consequence be of a seized saddle? This figure just illustrates the point. So we have the main chain span on one side of the saddle and the land chain side on the other, which is fixed at the land saddle. And the rollers allow freedom of movement, so these horizontal forces balance on either side. But you'll notice I've drawn the roller on an inclined plane. That's exaggerated. It's actually at a slope of 1 to 31. But it means that there's a relatively constant horizontal load on the towers trying to push them into the Clifton Gorge. I'm going to refer to this as load case 1, and Bob will pick up on the significance of that in a moment. But this is the doomsday scenario that the saddles seize. And all of a sudden, any changes in the main span due to live load, or more importantly, changes in the back span due to temperature, expansion and contraction of the land chain, bring the stiffness of the tower and the stiffness of the foundations into play, and the potential for generation of very large horizontal forces. And at this point, with the link between the structure and the foundations, I'd like to pass over to Bob to talk about the work that he's done over the past 10 years.
Thank you, Aegon, and thank you, John. So the focus now is on the bridge foundations and the associated slopes and the bridge anchorages. And I shall get started. Okay, so just an aerial view of the dramatic setting of the suspension bridge, spanning as it does over the river Avon, which flows downstream towards the north to the Bristol Channel in the distance there, and upstream to the south to Clifton Docks. To the west is Lee Woods, with the Lee Woods abutment, and in the foreground is Clifton. Many of you will know that the structural design, the bridge concept, was a compromise. Brunel would have had the Lee Woods Tower situated at the top of the relatively subdued Lee Woods slope with a longer span, but the compromise was to reduce the span, and the result was that Lee Woods was constructed partway down the slope and risen up with a large masonry and brick structure. Also, the compromise meant that the Clifton abutment was perched right on the edge of the precipitous rock face, which is 70 to 80 metres high. So the question is whether or not the compromise to increase the perceived safety of the suspension structure compromised adversely the stability and the stability reserve of the foundations and the slopes beneath them. In plan, you can see that the Clifton abutment is actually constructed on a promontory with a slope to the north the north slope, and the main gorge face, the south-west facing slope. And to the south, a west-facing slope with a relatively subdued slope profile. The underlying geology is Carboniferous limestone, the Clifton Down limestone. It's a sedimentary sequence laid down in layers, and the layers include interludes of what's called argillaceous material or clayey material, and you can see this forms prominent bedding partings which are very persistent throughout the slope width. There's an example. There's also through-going subvertical structure, and you can see the trailing edge of a joint set that trends perpendicular to the bridge, and this subdivides the rock mass into a series of slices perpendicular to the bridge. And in addition, there is a third set, you can see a trace there, which is more or less parallel to the bridge, joint set 2. So 3 sets of through-going joints or discontinuities that subdivide the structure of the rock. And it's no coincidence that the main subvertical structures are parallel to the main slopes forming this promontory, with the bedding dipping towards the south at about 30 degrees. So after that short overview, the structure of the talk will be initially visiting the rationale and the basis or the justification of why the technical committee of the trustees, and particularly ALF, felt it necessary to commission this assignment. And then I'll describe the geological and rock mass models that we developed as a basis for subsequent overload analyses to establish the stability reserve in the foundations and the chain anchorages. It's worth pondering for just a minute on what gave Brunel the confidence to position the abutment quite so close to the top of this tall, steep rock face. And it may be that he shared the prevailing view of the time, and that was that rocks were divine creations, and what was there now would always be there. And that was reasonable. The first geological map of Britain had only just been produced, and when construction started, this was more than 100 years before soil mechanics, rock mechanics, engineering geology, and the general practice of geotechnical engineering had started. And maybe he was right, because no movement has been detected in the abutments at Leewoods or Clifton. But that's not the case for the slopes to the north and south of both abutments. Starting to the south of the Clifton abutment, Clifton here with the high rock face, you can see immediately to the south, the rock face has gone. In the past, the slope has failed or degraded by some mechanism. There has been some quarrying since, but overall the slope has failed and gone. And then when we come a little bit further south, the rock face is back. And in the 1960s, Dr. Henkel was invited to come to site and to investigate why the portal structure of the Avon Rocks Railway, which is in tunnel up to the hotel at the top, why the portal structure had moved out by about 100 millimetres. And he worked out that the overall movement was out into the gorge, and he worked out that the main culprit was an underlying clay layer that formed the basal surface for the movement. But what he found when he plotted this up in cross-section, that the main clay layer, the main bedding, was zero apparent dip in this line of section, with all the dip towards us at about 30 degrees. So how was he getting movement out into the gorge? And he was really the first person to establish that it is possible to get oblique sliding on a bedding surface. And the reason for this was that the sliding happens on the intersection between bedding and an oblique structure. The problem he left us with is that our through-going structure, joint set 1, is parallel to the gorge and joint set 2 is perpendicular, and there is no through-going structure apparently in that orientation. Bedding causes instability throughout the gorge, and it's very evident. In the distance here you can see these surfaces dipping out, originally undercut by the river with a bit of quarrying since, and you can see the failure that has happened. And going back to the overview, so we were just looking at these slopes here, but looking at the natural slopes, you can see you've got a natural dip slope there following bedding, a scarp slope, And then in the Nightingale Valley, it's all completely asymmetric with a dip slope here following bedding and a steep scarp slope on the other side. And it's easy to see why the bedding has had such an influence when you see how polished and smooth the surfaces are and often associated with clay. It's also worth noting that these slopes that we've just been looking at are here where the river cuts round to the right and has undermined these slopes in the past, and the way in which it curves there is very similar to the way it curves immediately to the south of the Leewoods abutment here. It's not just bedding that causes problems with instability. This is immediately under the Clifton abutment, and you can see the through-going persistent joint set 1 structure, dividing the rock mass into a series of slices, and you can envisage this perhaps as a row of books on a bookshelf with the abutment constructed on the last few books. The joints also, like bedding, vary in nature. This picture is about 10 metres below the Clifton abutment, and you can see the mudstone and clay infill to the structure. The trailing edges that I mentioned of the joint set 1, where it is broken back here and here, give rise to localized block instability. And you can see this dangerous looking block, and it was this kind of view that led to the construction of the canopy over the road, the portway, below the Clifton abutment in the 1970s. And the joint set 1, this is just further downstream, can give rise to larger scale instability. It's not just the discontinuities, the joints, that cause problems in the gorge. The sequence is tilted at 30 degrees because it's folded, and if you walk from the docks into the gorge and start walking north, you go back from the younger rocks into the older rocks until you get to the bridge. But if you keep walking, the sequence begins to repeat itself, and this is because there are large thrust faults. This section has been thrust over this, so you've got older rocks over younger rocks, and this is immediately to the north of the bridge. So you've got the relative calm and tranquility of the 30-degree dip of this raft of rock that is relatively undisturbed, but immediately to the north you've got a series of thrust features. And if you stand on the Clifton abutment and look north, particularly on a wet day, you have these very sinister looking dipping surfaces that have given rise to deep-seated instability in the slopes in the past. Just briefly at Leewoods, there was a borehole investigation done in the 1960s, and the paperwork that we have seen for this recorded, not surprisingly, clay layers within the boreholes. But the same paperwork concludes that they were unable to correlate the clay layers between the closely spaced boreholes, which is odd. And a possible explanation is the St Vincent's rock fault, you can see in plan here, wanders underneath the alignment of the bridge and goes very close to the Leewoods abutment. And it's very difficult to map this. This is where the published map places it, but you could see that it could easily pass under the abutment structure. So it was the knowledge of this history of instability, and particularly Alf's knowledge and his local knowledge of the instability in the gorge, that led to us being commissioned to assess the stability reserve, and this is how we've gone about it. So we've produced geological and rock mass models that have formed the basis of the numerical analysis, and when we do this we try and place each discontinuity in the model in its correct position relative to the other discontinuities and layers. The published sequence of the sediments, the stratigraphy, is well known, but in terms of providing detail on a bed-by-bed basis, in other words, where are the clay beds, for example, it's not available. So we did what we could with the available outcrop, which we mapped and surveyed, and we catalogued all the through-going structure and gave them each a unique reference number, and we did that with the sedimentary sequence as well. We then undertook a borehole investigation with 3 boreholes at each abutment, and they were orientated so as to intersect each of the through-going discontinuity sets. So this one, for example, parallel to the alignment below Clifton, intersecting the through-going joint set 1 structures. And we did the same at Leewoods. And we found that, not surprisingly, within each joint set, there was a huge variety of joint types, from very strong heeled structures through to mudstone and clay infilled structures. So we produced a classification for both the bedding and for the subvertical structure, which varied from limestone contacts all the way through to the clay layers. And we assigned each of the discontinuities recorded and recovered in the core to one of those classifications. And that allowed us to produce these strip logs. This example here is recording the clay layers. And based on the sequence, and in particular the clay layers, we were able to establish a correlation between the boreholes and between the boreholes and outcrop in a three-dimensional interpretation. And we did the same at Lee Woods. And we were able to establish a correlation of this detailed sequence across the gorge, and by some remarkable coincidence, at the centre line, the base of the abutments are located at almost exactly the same height above the same bed E. We also gathered physical data for each of the discontinuity types, in particular the joint roughness and the joint wall strength, and that allowed us to, using the Barton-Bandis failure criteria, to develop a stress-strain relationship for each of these discontinuity types. So you can see the very weak compliant clay layers versus the very stiff limestone contacts. And this relationship, the Barton-Bandis model, was used within the numerical analysis that followed. And we verified this with a whole array of laboratory tests on the discontinuity types. So we ended up with a model, still in AutoCAD, of all the discontinuity types, the through-going structure, fully characterized with their geotechnical properties. Looking at the same model in long section, we found that the distribution of the joint types, particularly for joint set 1, was not uniform, and there was a concentration of the clay-filled joints, you can see a prominent red one there, and there are several others, were within what we called the central abutment zone. And this coincided with this valley feature, this natural valley feature that the abutment had been built up from. And we then had an outer abutment zone and a rearward abutment zone. And this formed the model taken directly into our numerical analysis called UDEC. And this is a distinct element model whereby the blocks of rock are free to rotate or fall, restricted only by the shear strength of the discontinuities around them and the forces applied. And we did the same for Lee Woods. There was a number of failure mechanisms that we have considered. I won't describe them all, and we'll focus on here the main gorge face and a particular mechanism, either toppling or buckling, that we'll look at. There were a whole rake of other mechanisms associated with the west slope and the adversely dipping bedding in this direction, which is essentially encompasses the Henkel problem. So we applied groundwater pressures within the model, so they were run under effective stress, and the groundwater here is compartmentalized based on our observations in the boreholes and in outcrop, perched on the clay layers and confined, so it doesn't drain into the gorge slope, confined by the vertical aquiclude, if you like, of the central abutment zone. And we applied the two load cases, LC1 and LC2, with the locked saddles as John outlined. And we ran the model. Initially, we run it without the gorge excavated so that it consolidates and in situ stress is established. We then excavate the gorge, build the bridge, and apply the loads, and then allow it to run. And this is the LC1 case, the standard bridge loadings, and you can see that the highest movements were at the top, reducing with height. And this movement was accommodated by shear displacement between along the joint set 1 structure. And if you go back to the analogy of this as a row of books on a bookshelf, if you push those books, the only way to get movement is if you have shear displacement between the books. And that's a classic topple failure, and that's what this was showing. We then began to test this to establish a stability reserve, and we first looked at upper bound and lower bound geotechnical properties and we got a very uniform distribution in the displacements. However, when we began to look at the distribution of load, the maximum principal stress plotted here underneath the tower with this load case, we realised that the outer abutment zone, the very, very outer part of it, shown here in the blues and the light greens, was essentially de-stressed through lack of confinement and was unable to carry any load and was effectively throwing it back inwards, if you like. Meanwhile, the central abutment zone, with all its weak compliant structures, was also deforming and therefore also throwing the load forwards into this narrow rib of rock, which you can see it's only about 5 metres wide, and it's carrying the lion's share of the load from the tower. So we tested it further, we doubled the loads, so this is LC1 times 2, and you can see remarkably that the displacement more or less doubled, which gave us confidence that the model equilibrated and didn't fail. It gave us some confidence that we were establishing a reasonable factor of safety. We then combined the LC1 times 2 with upper and lower bound, and now with the lower bound, with this load case, the model didn't equilibrate, it fell over after about 60 millimetres of movement. But it gave us still some appreciation of the limits of stability under this particular mechanism. Under the LC2 case, the model failed immediately. We did the same for Lee Woods, and so this allowed us to do a comparison with the same load cases between Lee Woods and Clifton, and this gave us some assurance that we weren't exaggerating things at Clifton. We hadn't underestimated geotechnical properties, because you can see even for the LC2 case, the Lee Woods had very little movement at all. During this time, the vegetation had been left originally for good reasons by the trustees, but for various reasons it was decided that that should be cleared, and from a geotechnical point of view the reasons were clear. You can see a mature tree here, stump that's left, and the roots from it, and it had prized this large block of rock off, and this was the next bit to go. So there was a programme of clearing all the vegetation from both the gorge slopes and the north face, and this afforded to us a new view of the joint set 1 structures that we'd only seen in boreholes previously. This is a close-up of that main red joint that we've seen before. And it also allowed maintenance inspections. This masonry infill has now been improved and the pointing done as part of the overall masonry work that Egan described. We also at this time had access into the abutment itself. Like Lee Woods, this abutment also has chambers that you can access, and the next photograph is taken from about here, looking down into this valley feature. So this is the inside of the masonry wall we were just looking at, and to the right is masonry that directly underlays the tower. So unlike Lee Woods, where the tower is supported on the top of the abutment and the abutment is part of the structure and the foundation, here at Clifton the tower is founded directly on the rock, and the abutment structure is more of an apron around it. So we now had an updated model in terms of the foundation. We were able to survey in the location of the key joints, the central abutment zone, and we found that these were actually located 3 or 4 metres in from the slope than we had originally modelled. And it doesn't sound very much, but of course that means that the rib of rock that we're relying on to carry the load was significantly, in percentage terms, wider than we had first envisaged. Also at this point, which was January 2016, we were asked to consider the capacity of the anchorages, and I'm now going to briefly outline where we've got to with that. So the land chains coming down from the tower are connected to a land saddle. The land saddle is founded on a cast iron plate directly on the ground, and the anchorage chains are connected there from the saddle down into the anchorage tunnel, which is about 20 metres long, and they're fixed in place with a Staffordshire brick plug, and fastened with cast iron anchor plates and webs. And because of this deviation in the cable angle, there is a large force directed into the ground, a bearing pressure underneath the saddle, and that's very good for applying confinement to the rock, because the rock strength is stress dependent and confinement is good. And the same thing happens in plan. This is a plan view of the brick plug, and you can see that it's actually markedly arched. And this is good because the main forces are then directed into the rock, and you can imagine that if you have parallel to joint set 2 structures, as we do, this will apply a significant normal force across them. So we applied loads in this model at the tower saddles in the same way and at the land saddles, and we modelled the anchorage chains and their brick plug. We did it in a 3-dimensional model. This is shown here, and we managed to get quite a good level of detail into this numerical model of the structures and the geology. So in terms of possible mechanisms of failure of the anchorages, there were 3 that we were considering. One is a joint-bounded block, joint set 2, joint set 1, and bedding underneath, that essentially would be extracted under the anchorage loads, rather like a tooth being extracted. The next is a little more complicated, and this involves oblique sliding along the joint set 2 structure into the north slope, which is not very far away, with our bed E forming the basal surface. And the last one was shear displacement along the subvertical joint set 2s, but offset by the joint set 1s to form this sort of sawtooth profile, which with this mechanism, if it happened, would then mean that loadings from the anchorages would be completely interactive with loads and the effects of the loads from the tower. We ran the model, the 3D model, in a very similar way to the UDEP model we'd seen previously, and we applied a load factor just to the live load at the land saddle, and ran the model. So this is 1, 2, 4, 6, 8 times live load at the land saddle without groundwater pressure. And this showed us that essentially we had all 3 of the mechanisms playing some part. You can see here, this is the anchorages sitting in here, and you can see this joint-bounded block, a prominent joint set 2 there, and almost all of that movement, and the movements before the model failed were very, very small, but the majority of that movement was vertical. But there was a small amount towards the north slope, but that didn't really develop as a failure mechanism. And it's hard to see on here, but there is a sawtooth profile which allowed the deformations to develop all the way from the anchorage to the tower and interact with the behaviour of the tower. These are cutaway models looking from behind, and you can see the anchorages structures there. That's total displacement, and this is vertical displacement. So you can see the idea of the plug being pulled out is real in terms of the modelling, at least. So based on the results of this, we've been able to relate the loads developed for each of the failure mechanisms and establish an overall factor of safety for each. And we're in the basis of concluding this at the moment, and managing to put a big tick against the stability reserve for the Clifton anchorage, at least. We're revisiting the toppling failure because of the narrow rib with the updated model, and so we hope soon to be able to put an equally big tick against those. And we've also been working our way through all the other potential mechanisms of instability, and putting ticks where we can and following up any loose ends where we need to. And we've done the same for the Leewoods abutment, and we did the same for the Clifton North slope. So just my last slide. It's been a team effort, this geotechnical study. All the numerical analysis was led by my late colleague Stavros Bandis, who passed away about a year ago, and this has been followed up by Elias, who has been leading it since, and a lot of that work that I've just presented was done by Elias, supported by Michael. Everything has been reviewed by my senior colleague, Dr. John Sharp. Mike Summers has helped a lot with the development of the geological models, and we've been consulting with John Cosgrove from Imperial College on the Henkel problem. All the work has been independently reviewed by peer reviews appointed directly by the trustees, Mike De Freitas has reviewed the geological and rock mass models, and Bob Pine the numerical analysis. Thank you very much, ladies and gentlemen.